So now we're going to do another video that I find really fun. So this is a circuit I made in the last video. So I have the oscilloscope connected there. You can see it drops down to 0 volts. For some reason, when I have it at this frequency, the 0 volts is down there. Let's zoom in to that really quick. So that's 20 milliseconds. That's for each division right there, each square. And if I turn this dial, because you can see that's where we have the setting, if I hit the button again, it changes that up there and it goes down there. Sometimes if you hold a button for a couple of seconds, it does something else, such as the display there. That goes away when you hold OK for a little bit right there. And if you want it back up, which I do for whatever reason in this video, you hold it down again. So 20 milliseconds or less, or I should say or faster, then for some reason the 0 volt is down here where the purple one is. We will turn the dial so counterclockwise, 50 milliseconds. Now you can see it went back up there. So the longer we make each division there, for some reason above 20 milliseconds it is up there. Now let's go back to 20 milliseconds per square there. You can see it drops back down. So I don't know why it does that, but it does that. So the last circuit we did, it's still on the board here. We have, get that glare off there, we have this MOSFET transistor switch. So there you can see the voltage shot up. Looks like it shot up 5 volts. And we release it. Now it goes down to 0 volts right there. We have the black probe to the oscilloscope here. An alligator clip comes off of that cable there. So I have a clip here with a jumper, negative rail. We are taking our voltage reading with the red alligator clip up at the drain of this P channel MOSFET. And you can see the voltage there. So in the last video I did where we built this circuit, we looked at falsely triggering this. And I can really easily do that with my fingers touching the metal. And sometimes I don't even have to touch the metal. There we go. I'm not even touching the metal. You can see it's a different waveform. It's kind of an interesting waveform. But current does not have to flow through the gate of the MOSFET transistor like the bipolar junction transistor does. So all I really have to do is apply a voltage. There's a slight shift in current, but it's kind of like a capacitor where it kind of charges and discharges. So no current really flows through gate to source in any meaningful way. It just kind of wobbles back and forth, kind of like a capacitor charging and discharging. But that is just my body. So one interesting thing, and we looked at this with the bipolar junction transistor as I said before, but it was not this effective. This one's really sensitive to the voltage my body can create. But you may be wondering why my body can't create that. You can see that is 60 hertz. That's what I'm generating. So that is the frequency of the power of the household power that we use in the United States, in North America I should say. I think it's 50 hertz most of the rest of the world, but 60 hertz here in the United States. That's how often the current in the wire goes one direction and then the other. 60 times goes one way then the other, 60 times a minute, which is 60 hertz. And so you are seeing that right there. Now of course I can let go, and we'll also do this. I might be able to get it on and keep it on. There we go. See, I got it on and keep it on. I'm not touching anything conductive, touching the plastic here, which does seem to influence it. So now let's look. You'll notice that it's not fully bright. When we have the square wave, it's a bit dimmer. That's because it's off somewhere about half of the time. In fact, we can look at the duty cycle. It says 51.3%. So that means it might be on just a speck more than an off, but also I think it's just the way the meter measures it. So watch the brightness of the LED. I'm going to touch it to this jumper, which goes to the negative rail, while I'm also holding it. And you can see the LED got brighter. So it's dimmer when I get away from the jumper, when I give it a fully negative signal, because it is a P channel MOSFET. When I give it a negative signal, it is on fully. When I'm giving it a signal with my body, instead of the negative rail, it is on about half the time and then off about half the time. So when we have a high output, my body is giving it a low signal. When we have a low line right here, that means my body just gave it a high signal. You can tell because if I go to the negative rail, you can see that the wire jumps up. If I put this to the positive rail, it goes down. So, in any case, I find this kind of stuff fun. These oscilloscopes here, they're DSO shells. They're not very expensive. I believe this was $40 if I remember right, probably like 42. And so not terribly expensive, but as you can see, it's pretty useful in my opinion. And somebody really obsessed with oscilloscopes might not like it, but of course they're going to pay a lot of money for a really good oscilloscope. For this price, I think this is a great oscilloscope, and I never used a great one to compare it with, but this takes care of everything I want to do for my videos, and so I like this one a lot. So in any case, this is just kind of a bonus video. I find this fun dealing with the signal from my body, plus later on you might be working on a circuit where you'll notice something like this, 60 Hertz right there, and you'll realize maybe something came loose going to the transistor or something, so it is oscillating like that. And so you never know. The more you learn, you never know in the future how you might apply it, but somewhere along the line it's probably going to come useful, every single thing that you learn. So thanks for watching, and I will see you in the next video.